Hi, this video is a part of Deep Learning with TensorFlow playlist. In this playlist, I quickly explain the logic and implementation of deep learning algorithms and applications using TensorFlow. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that people can read the notebooks and re-implement them yourself. Code files for each video will be given in its description, so I'm expecting my audience to have good understanding of deep learning and they just need little hints for implementation of deep learning algorithms using TensorFlow. In this video, I'll talk about generative adversarial network-based phase generation. GANs is very interesting and powerful idea. In GANs, we have two types of network. One is a generative network and another one is discriminative network. Generative network tries to generate images from random noise, completely random noise, whereas discriminative network tries to discriminate between real and fake images. So, what is this idea? How it works? Let's jump to the whiteboard and notebook to understand the idea in better way and code it in Python. So we are having these two different networks. One is discriminator, another one is generator. Okay, let's look at this discriminator. Given these two images, these are real images and these are fake images generated by generator. Now, given these two images, the only task of discriminator is to discriminate between these real and fake images. So this is simple CNN classifier. Now, understanding of discriminator is quite simple. So this is simple CNN classifier. So inside this discriminator, we have this convolution operation and this pooling operation, as we have done it in regular convolutional neural network classifier. However, the problem or the technical detail is in this generator part. So we have this random noise. Given this random noise, what we want to do is we want to generate this image. How will we do? We will use this deconvolution operations. Now, this deconvolution operation is completely opposite to this convolution operation. In convolution operation, what we are actually doing is that given this image, we are reducing this input image into smaller dimension and finally into two different arrays, a matrix of samples, and there are two columns. One is giving us the probability for real and another one column is giving us the probability for fake image. So this is for each of the sample in this discriminator. So in a way, we have this matrix of numbers that we get output given this image. And how do we do it? By applying these convolution and pooling layers. Okay, in this generator part, we are going in the opposite direction. We are having these numbers and we will apply these deconvolution and upsampling operations, which is opposite to pooling. This upsampling is opposite to pooling and deconvolution is opposite to convolution. And from this matrix of number or a numpy array, these are simple numbers array of random noise, this is a random noise, we generate these images. Okay, inside this discriminator we have all of these, there are a lot of weights, and inside this generator we have a lot of weights. Okay, now our task is to learn the weights of this discriminator to be a good discriminator so that it could discriminate between real and fake images, and the task of generator is to learn the weights in such a way as to find out those weights which could befool this discriminator. So this generator task is to generate fake images in such a way so as to fool this discriminator in thinking that this fake image is kind of a real image. So this is a min-max operation if you're more comfortable with this AI terminology. So this is a min-max operation. One network is trying to minimize and another network is trying to maximize. So we want to find out that balance. So two opposite tasks are done. One is trying to discriminate while the other one is trying to befool it, is trying to make it think that the generator images which are basically fake, but this generator is trying to create images, create an illusion that these fake images are not fake images, instead they are real. How do we do it? Let's look at a bit technical detail. These GANs are look very difficult, but they are really simple. As I've already explained that this discriminator is a CNN classifier, but the loss is actually an addition of two different losses. One is the loss for given real image, and another one is a loss given fake image. So both of these losses will be added together, and this will be the loss for our discriminator. And for generator, we have only loss for these fake images, and this loss will be calculated from the discriminator. So in a way, what we are doing here is, just let me change the color. What we are doing here is that we will, for discriminator, we are having these two losses. One is the loss for real image, another one is a loss for fake image. So both of these losses are added together and then used to adjust the weights of this discriminator. However, in case of this generator, we look at the loss for fake image, and this loss of fake images is then used to adjust the weights of this generator. Why? Because we want to adjust the weights of generator in such a way so as to generate images to fool this discriminator. I hope so it makes sense. I mean, the last function also makes sense. Why? Because we want to befool this discriminator in thinking that this is not a fake image. Instead, it is a real image. So we don't want discriminator to categorize our fake image as fake. So that's why we take this loss, and based on this loss we do backpropagation and adjust the weights accordingly. So with number of epochs, the weights will be adjusted in such a way so as to generate the images which will basically be fake. However, the loss will be minimized for fake terms. So this discriminator will be difficult for discriminator to discriminate between real and fake, because these images will be more like real, because we are adjusting the weights in that way accordingly. So for that reason, one bit of technical detail is that while training, we will train discriminator for five epochs, and then after 5 epochs we will train generator for only 1 epoch. Why? Because we want to train discriminator more. Because the more it is kind of a hyperparameter, and there is a lot of technical detail in tuning these values. But however, we will train discriminator a bit more. And then there is also idea of using different optimizer for training these different networks, this discriminator network and generative network. These technical details and these nitty-gritties are kind of really difficult and kind of a bit annoying, and it is more of an art than a science. However, the main idea is really simple, where we are having all of these losses and we use these losses to adjust the weights for discriminator and generator. So this is a technical detail that I've already explained. Now let's jump to the notebook to understand this idea and code it in Python in better way. Okay, so we begin by importing all the necessary libraries. Then we load the dataset. This is like faces dataset. Then we divide it by 255. So our range of values are between 0 to 1. And then what we will do is we'll show this is one of the image that we will be working with, and we'll be trying to generate these kind of images at least. So this is how randomized generate these faces. So that's why these GANs are also called generative model, because they are generating images. Okay, now how do we do it? The first part is a generative network part. This is generative network part. This code size is basically 256. So from 256 random numbers, we will generate this image. How do we do it? We will do it using sequential API of TensorFlow, having input layer of size, code size, which is 256, and then we will convert it into 3-dimensional, because we want to generate 3-dimensional images. These are three-dimensional images. Why? Because it's RGB. There are RGB values also involved into it. Okay, then what we will do is we will reshape. After reshaping it, after applying this dense layer, we will reshape it. After reshaping it, we are just applying this deconvolution operation 2 times, and then we are applying this upsampling operation, and then again we are applying this deconvolution operation 3 times, and then we are applying this con2d. And finally, if we look at the summary, so we are having these 640 numbers, and these 640 numbers are reshaped into 8, 8, 10, and then after applying this deconvolution, we are having this NumPy array, or this architecture, or this layer containing 12, 12, 64 parameters. These are all multiplied to get a value of 16,064. And then after again deconvolution, this image is actually dimensions are increased from 12, 12 to 16, 16. Then after upsampling, we get 32, 32, and then again we are deconvolving it, and again deconvolving it, and again deconvolving it, and after deconvolving we finally convolve it. So this is our final image of size 36, 36, 3. So from this 256 code size, what we have done is we have generated this 36, 36, 3 image. And in the process, we applied this dense layer, we reshaped it, we applied this 2D convolutional layer, this upsampling layer, and again these deconvolutional layer, and again finally we applied this convolutional layer. So this is how we move from small hidden unit layer to a complete picture. So this will be a complete picture having dimensions of 36, 36, 3. Now, what will the discriminator part do? In the discriminator part, we will be having this input layer of image shape, whatever the image is of shape, image shape is, and we will be having this image shape input layer. We will be applying this con2d layer and max pooling, and this combination will be applied for next 2 times, and then we will flatten the layer, and then we'll apply this dense layer having 256 nodes or hidden units, and finally we'll apply this dense layer of 2 units. So we are actually outputting these final 2 probabilities for real and fake images. Okay, so this is the discriminator layer. So having this input, we apply this con2d layer. After applying this con2d, we have this dimension of 34, 34, and then we have 17, 17, then 15, 15, 7, 7, 5, 5. Filters are increasing. This channel depth part is increasing, and this height and width part is decreasing after each operation of con and pooling. So finally, we get this 2, 2, 128 filters, and 2, 2 are actually height and width dimensions, and then we flatten all of these values. So we multiply all of them together to get this flattened single dimension value, and then what we do is we apply this dense layer of 256 units, hidden units, and then we finally apply this 2 units to get this 2 values. Okay, for real and fake images, these will be the probabilities, final probabilities. Okay, now the training part comes in. In the training part, what we will be doing is, so first of all, these functions are important to understand. We have this random normal function, so this is generating random noise from normal distribution having size batch size comma code size. Code size is 256, as I've already explained. This is the code size, and batch size is the number of samples that we want to use in single batch. So these are this will be a matrix, a numpy array of size batch size comma code size, and this will be a numpy array, a matrix of total number of samples that we want to use, and the size will be equal to batch sizes. So these are total number of samples or total number of images in a batch. So these suppose we are using a batch size of 128, so we will be sampling randomly from our training data set 128 images. So this is a sample, this is a function for that, and these are sample images. How do we sample images? We are using this sample nice batch function to give input a complete noise, a complete random normal noise coming from normal distribution as an input to this generator, and this generator will predict using this random noise in image. As I've already explained, that inside this generator we are applying these decon operations again and again to come up with these images. So once we have these images, then we will plot them, and for finding the sample probabilities, what we will do is we will look at the discriminator network, and we will use this discriminator network to predict, given this sample data, these sample images, these real images. So once we have that, then we will also look at the discriminator network taking input these generator images, these fake images. So for the first time we are getting input these real images, and in the second part we are getting these fake images as an input for the discriminator, and we are also applying this exponential function because we are having multiple classes. Okay, then what we will be doing is that these are just functions that we will be using later. This first function is used inside generator, so this will be used as a function, as a input for the generator. This second function is used as an input for the discriminator, and this third function is used to generate images given the generator network. So this generator network will take this first function as an input and then generate fake images, and inside this function we will be sampling and we will be generating the probabilities for both the fake images and the real images, given for both the real image and the fake images. Fake images are those images which were generated by this generator. Okay, once we are done with that, then this is what we are sampling. This is nice and this is real data, and these are just matrices. Once this is given this real data, once you apply this discriminator network, we get these final probabilities for real class and this fake class. Okay, after we are done with this generator network, which is very simple, which is doing simple CNN classification, let's look at this generator network. This generator network is taking noise as an input and generating these images, 100 images of size 36, 36, 3. This is the dimension of a single image. So we are generating 100 different images because the noise were generated, the batch size was of 100. So we generated noise for 100 different samples. So from all of those 100 samples, we generated 100 images of dimension 36, 36, 3. Okay. Then what we will be doing is we will be applying this discriminative network for all of these 100 fake images. So given this generated data, we apply this discriminator, and we also look at this loss of fake images. So let me reiterate, this is the loss for real images, this is generating fake images, this is the loss for fake images. Okay, once we are done that, let's use final function. This is the function for discriminator loss, where we are adding this loss for real images and generated images. This is addition of both the losses, and this is basically the optimizer for discriminator, and this is the loss that we have used. And for generator, we are using a loss of only generated images, as I've already explained. This is once we have done, we have defined these loss functions, then we will apply this optimizer atom optimizer again for generator, and we have also applied this atom optimizer for discriminator. And once we have applied this once we have defined this lambda function containing this loss for generator, so what we will be doing is we will be applying this for 50,000 epochs, and for each epoch we will be adjusting the weights for discriminator 5 times, and we'll be adjusting the weights for generator only 1 time. So this is how it is done, and from complete random noise, these were some of the images that we actually generated. Okay, now after this may take some time, so it will even if you are having GPU, it will take some time. These images are not perfect images because I was not able to because my computer's power is not that much enough. You could train it on cloud using multiple GPUs, and you could have very great results. NVIDIA's results are really powerful and are really fascinating. They generated very real-like faces because of their computation and their tuning of the network. Nevertheless, we have generated these faces using both of these networks, discriminator and this generative network, and these are some of the samples that we got out using our generator after learning the weights. I understand that the lower parts are not really good, are really cool. However, the eyes and the noses have been learned very in a very fascinating way if you look at it. It is kind of scary, but still we were able to learn it. And you can increase the epochs, and you can tune the network, and you can read different papers to tune the networks to come up to a better solution. Let me just reiterate what we have just done. The whole idea is really simple. We just have to do this deconvolution operations in this generator, and these convolution operations in this discriminator, and then finding out, then these functions are really simple. This is random noise. These are extracting out random images, real images. These are sampling different images given random noise from the generator. These are extracting the probabilities for both the real images and the fake images given this discriminator. And then these ideas are used to define these loss functions. And for discriminator, we are adding these loss functions, and for generator, we are not adding these loss functions. Instead, we are having only loss function for the fake images. The output probabilities that we have received from the discriminator using fake images, this will be used as a loss function. We want to reduce this loss function because we want to fool this discriminator. I hope so this makes sense now.